Hey everybody, this is our lesson on Newton's first and second laws. And by the end of this lesson, you should be able to explain the forces used in Newton's three laws. We'll look at the third in the next video. But these are all laws of motion. So first, let's talk about Newton's first law. We'll start from the beginning. And he summarized this study of force and motion in several laws. Again, we're only going to focus on 1 and 2 in this video. So the first law of motion states that the state of motion of an object does not change as long as the net force acting on that object is zero. So if there's no opposite force or counteracting force, the motion of that object should not stop. If it's staying still and there's no force applied to it, it should stay still. If there is a moving object and there's no force applied in the opposite direction, it should keep moving. An object that's in motion stays in motion, if you've heard it that way. So unless an unbalanced force acts on that object, then it should remain in whatever state it was in originally. So an object at rest and an object in motion remains in motion with the same speed and direction. If an object's at rest, it will stay at rest. So that's probably how you've heard it, is an object in motion will stay in motion. Forces will change the motion of the object in specific ways. So you see this little GIF here, those balls, if you've ever used those, I forget what they're called, but they will continue to hit together for a very, very long time. Eventually they'll stop because there is a little air resistance that plays a factor, but very minimal force on those, so they will continue to move back and forth. A lot of times I use an example of like a soccer ball. So if a soccer ball is still on the soccer field and there's no force applied to it, it's going to stay still. But as soon as a player kicks the ball, it's going to be moving. However, if it rolls across the grass and no one messes with it as it's rolling, it will still eventually stop, but that's due to friction applied on it from the ground and the grass, that rolling friction. So here you go. A ball resting in the grass remains motionless until a force is applied from a kick. And then because there's friction between the grass and the ball, it will roll until it slows down and eventually stops due to that friction. The force of friction will slow that ball and then stop it. So I like this little picture over here. Just, that's the law of inertia. So the first law is also referred to as the law of inertia. So let's make sure we understand what that means. And this is the tendency of an object to resist change in motion. So that means it's going to keep doing what it's doing unless a force is applied. So here, this person running with that ball would keep running if they didn't hit that brick wall of another person that slings them all the way back. An object at rest tends to stay at rest, and an object in motion tends to stay in motion. And the object in motion will keep moving at the same speed and in the same direction if no force is applied. The velocity of the object, again, should also remain constant because we shouldn't change the speed or direction. An object at rest will remain at rest as long as there's no force applied to it. All of this should make sense. All of these are ideas that you've seen before. So rest here, we will define that as a case where the velocity is equal to 0. And then the more mass an object has, the greater its inertia, so the greater its resistance will be, which should make sense because if you look here, the person running is a lot smaller than the person that they hit. So the inertia of the larger person is stronger than that of the smaller person, which is why the smaller person gets flown back. And the greater the inertia, the greater the force will have to be to change its velocity, which makes sense. So now let's jump into Newton's second law. And this says that the acceleration of an object increases as the amount of net force applied from the outside on the object increases, which makes sense. The more force applied, the more of that change that will occur. Objects will accelerate in the direction of the force. So if you see this little GIF here, Wile E. Coyote, the force of that spring is stronger than his force holding it, which is why he slings back in the direction of that force. The amount of the acceleration is affected by certain conditions. So first, it's affected by the force. The larger the force applied, the greater the acceleration change will be. The mass. So the larger the mass, the greater the force that you'll need to move at the same acceleration as a smaller mass, which makes sense because the heavier you are, the more the heavier the object is, the more force that has to be applied to get it moving and get it going. The smaller it is, the less force you need. So they are inversely related. Okay. Larger bodies need more force, smaller bodies need small force. So I guess I should say directly related. Not inversely, directly related. The formula for force here for Newton's law is mass times acceleration. And the unit for force here is either a Newton, so you could do that, or if you forget that it's a Newton, you can see the actual parts put together, which is kilogram times meter per second squared, because acceleration here. And then remember, as we studied this in a previous lesson, a Newton is defined as the amount of force needed to give a mass of 1 kilogram and acceleration of 1 meter per second squared. So let's look at this example. It says how much force is needed to accelerate a bicycle and a rider with a mass of 60 kilograms at 1.5 meters per second squared. So we know we're looking for force. We know the mass that we're looking at, the cumulative mass that we're looking at is 60 kilograms, and the acceleration that we're trying to reach is 1.5 meters per second squared. Our formula is F is equal to ma, so we're going to just plug that straight in, and 60 times 1.5 comes out to 90 kilograms times meter per second squared, or 90 newtons. You can use either one there. So now go ahead and pause the video and try this example. What is the net force? What net force is required to accelerate a car at a rate of 2 meters per second squared if the car has a mass of 3,000 kilograms? So now let's talk about weight, which a lot of times people use weight and mass interchangeably, and we actually should not do that. Mass is the measure of how much matter something consists of. Weight is the effect of gravity on that mass. So we have to take into account gravity when we look at weight. That's why we are made up of a specific amount of mass, but we weigh a different amount here on Earth than we do on the moon. So this is used to refer to the gravitational force between Earth and all the objects near the surface. So that's what like our scales are measured in. The more mass an object has, the more weight it has, because it's the mass times gravity, acceleration due to gravity. This is also measured in newtons, which is the unit of weight and any other force, or any other force. Our spring scales are used to measure weight, so they take the effect of gravity into account. So this is known or calculated as F is equal to mg. And sometimes you'll see it like here, it's F sub W specifically, so it's the force of weight, which is mass times acceleration due to gravity. So let's look at this example. And it says for an object's mass of 30 kilograms on the Earth, what would be its approximate weight on Earth? So we know it's made up of 30 kilograms. Now we have to look at the effect of gravity on that 30 kilograms. So we know it's F is equal to ma. Our m is 30 kilograms. Our a is 9.8 meters per second squared, because that shouldn't change as long as we're looking at Earth's gravitational pull. So we put those together, and we come out with 294 newtons. Okay. Again, go ahead and pause your video and try this example. All right, guys, so now you should be able to explain and calculate the first two of Newton's laws of motion.